So thank you all for being here. Let me start sharing stuff. So what we're going to be talking about for the next couple of hours is basically an introduction to mechanistic modeling of bioprocesses. It's this workshop or this short lecture is meant to be interactive. So don't hesitate to interrupt me anytime. And I will be asking you to do some small exercises along the way. And yeah, so let's keep it dynamic. I know it's difficult online, but let's try our best. Otherwise, it's just gonna be me talking and waiting for somebody to say something when I ask questions. So what we're going to be talking about now is, first of all, what is a model? After the lecture of Yoram, that's going to be pretty easy for me. Why modeling? And then we're going to go through some of the most important concepts when we are developing a mechanistic model of a bioprocess. So things like mass balancing. And then we're going to go through the main two terms that you have in reactions in these models, which is basically stoichiometry, which comes back to a mass balancing issue, and the kinetics, which is what Yoram was mentioning right now with the Monod equation, which is the one that we're going to be mostly talking about today. I'm going to describe later on how we usually present these mechanistic models of bioprocesses, which is usually in a matricial form, which is called Goodyear matrix or Peterson, however you want to name it. And then we're going to go through an example with the ASM, so the activator/model 1. And then we're going to do a practicum, which I'm going to have to ask you again, your participation, otherwise it's going to be very boring because I don't pretend to do this again. So I expect you to do it. So please, at least for that part, switch on your cameras and open your mics. And let's see if we can do it interact, at least for the final part. So what is a model? A model is a representation of a system in any other form. So the idea is that we have an alternative view of a system that is useful for us for a given purpose. In our case, we use mathematics to make our models of our bioprocesses, which simply means that we do a mathematical translation of the reality, and importantly, at a given time, usually. When we talk about models, many times when we introduce these terms, we do it to people that are not very acquainted with modeling and mathematics, at least not very deeply. And generally, it instills a bit of fear, at least to step in. And we always say the same thing. A good model is built by someone who really knows the process well. It's not necessarily built by somebody who knows the mathematical tools well, which of course can help. But the very important thing, at least in these mechanistic models, is to actually know and understand a bit what's happening in your process. If you don't have that, it's very difficult to build a model in this case. And the most important thing, I will stress this many times, I will repeat myself all the time, when building a model, is why you are modeling. So what's the objective of the model? If you are doing it just because you want to do it as a learning exercises, okay, it may be good. But if you actually want to develop a useful model, the final objective is one of the most important things that you need to define. And classic sentence that a quote, I don't know if from George Box, but I guess most of us say that it's from George Box. All models are wrong, but some of them are useful, which is always true. In our case, if we want to talk a bit in mathematical terms, a model for us is a mathematical representation of a physical system for a specific purpose and experiment. That's generally the most simple definition of a model that we're going to be using here. So, as I was saying, I'm going to be repeating myself a bit now. If you want to understand why you're modeling, you always need to keep the final objective in mind. Otherwise, in many cases, you are neither going to be able to know the structure of your model, and you're not going to know why actually you're doing it. So it's something that is probably the first thing that you need to think about. It's not because you have data, it's not because you are able to make a model that you're going to do it. You need to think about why you're doing this exercise. There are many reasons, and I hope after this short lecture, you're going to get some motivation on why modeling. And a first very obvious reason is for operational purposes and for design. So when you have a validated model, first things first, it's a tool that enables you to test infinite scenarios, arguably, without needing to carry out experiments. So that's an extremely useful thing to do, because when your model is available, you can just simulate stuff almost instantaneously. And that's tremendously useful to guide operation of plants, of course, but also in terms of research to screen different alternatives if you are not sure or which way you want to go. This is a bit less intuitive, but there are many things that are very difficult to measure. And with models, we can estimate parameters and variables that are very, very difficult to measure. And that's extremely useful to also know and get more information from our bioprocess. So the flow of information goes both ways. It's not that you only create an accurate model because you know your process, but having an accurate model can also give you a lot of information to learn more about your process. It forces you to do precise mass balancing. And this is something that seems very obvious. It's not. And many times when we model, we face the case when somebody comes with data and they ask us or some people who have done models before if we can do a model with it. And of course, the answer is usually yes, because we like doing it. But the first thing that we realize when we start getting deeper into data is that mass balances are not closed. So when you want to develop a model, you really dive deep into your data. And for example, doing precise mass balancing is one of the main things that you need to do before you start even thinking about using experimental data for modeling objectives. Of course, you can use your model also to optimize your system and to control it. And also in link with the scenario analysis, you can predict how the system is going to behave, which is obviously very interesting, not only for control, but also to optimize the performance. Not only for operation and design, for research is also very useful. As I was saying before, being able to estimate non-measurable variables, for example, or parameters can explain some observed phenomena. And you can build your model doing some hypotheses that are very difficult to test experimentally and use the modeling outcomes to show that at least in principle, the hypothesis that you are using to build your model seems to be right. So that's something that is also not very intuitive, but you can do this kind of hypothesis testing through modeling exercises. Again, if you build a model based on a hypothesis on certain mechanisms or using some parameters that you're not able to measure, running the model and doing simulations can give you insights on the underlying system mechanisms. And of course, you can have fitted parameters that you are not able to measure in it. So mass balancing. I'm going to be repeating myself a bit on this. And at some point, I'm going to ask you if everybody is familiar with this. Most of you should be at this point. So we are going to assume in most cases that we are having an homogeneous and dilute CSTR, so continuous stereotime reactor, and volume V, flow rate Q, and concentration in of a given chemical species. And we're going to have the same thing on the outflow, right? If we do a mass balance, and this is generally what we want to do in these kind of models, what we want to know is how the system changes over time. And for that, we need to know what is the mass of a given component of the model that is being accumulated over time. This accumulation can be positive or negative. And how we do it is classic mass balancing exercise. So mass in minus mass out plus the mass produced or consumed. If we just sum all this out, you got the overall change on your system over time. If we put it in mathematical terms, this is generally how we see it. So differential on a given of a given mass over time is equal to mass in. So the flow rate times the concentration in the effluent minus the effluent plus multiplied by the concentration of the system, which is a CSTR. So the concentration in the reactor and in the effluent is the same, plus the reaction term. I will come back to this later. But this basically accounts for the biological reactions. If we don't have any biological reaction, it's just in minus out. But as we have those, this is what's going to be the most important term in our reaction loss, of course. Just to have an idea, I don't know, can you raise hands or something if you have all seen this before? Okay, one. Don't tell me it's only one. You can talk if you don't know how to raise hands in Zoom. I hope this is a mistake. Okay, more floating around. Okay, 5. You are 39. Okay, I'm gonna get out Jerome and Jeffy and Ellie and all these guys, but only 5 people out of 39 have seen a mass balance. Okay, this is gonna be a bit challenging. Again, if it's something that you don't understand and something that you want me to go back to, don't hesitate. Just stop me on the way and we go back to it. Okay? Because this is the very basics that you need to understand here. So this is the equation that I just shown. And what we generally do is we simplify and we assume that the volume is constant, which is fair enough for most of our reactors. And we have what we call the intensive form of our mass balancing equations, which is this one here. The only thing that we have done is we just get the volume out of the differential term and we divide all this by the volume. It's, we're going to assume generally steady state here. So as the volume is the same, Q in and Q out are the same. So Q in is the same as Q out because the volume is the same. Otherwise, it wouldn't be. And this is just saying that if we have many reactions, the reaction term overall is going to be the sum of all the reactions where our species C is involved. Okay. So I'm going to see if somebody has been listening to me so far, and I hope that more than 5 people actually have seen mass balancing before, because I'm going to ask you to fill this equation, these equations here. So what I can do maybe is I'm going to go through this ones first myself, and then I'm going to ask you to do a second one. Okay. So let's say that we have 2 CSTRs in series. What we have in the first reactor is just Q in, so the flow rate that goes into the reactor and the concentration of a given species, and the effluent from this reactor, which is Q1, whatever you want to call it, that is the output of the first reactor, so Q1 makes sense. And the concentration, which of course in the effluent is the same as in the system. Again, the volumes are the same, so all the flow rates need to be the same mandatorily, right? If we do the mass balance over this reactor here, what we want to see is the difference in concentrations in this chemical species over time. And if we go back to this equation here, so the intensive equation form, what we're going to have basically is Q in divided by V1 multiplied by the delta in concentrations between effluent and effluent, plus all the reaction terms that we're going to have in reactor 1, which is what this sub-index means. If we do the same for reactor 2, in this case, it's going to be C2, the chemical species that we want to model. I'm saying chemical species because I'm not putting any biology in here. And what we have is, in this case, the influent is Q1, so the effluent from here. And of course, we don't have V1, but we have V2, and the difference in concentrations in and concentration out, plus all the reactions that we have here. I'm going to assume, because I'm not hearing any comments from anybody, that this is pretty clear. So yeah, what I would like to do in the next 5 minutes to see if this is clear is for you to fill these two terms in. So if you understand pretty much what I just mentioned here, you should be able to do these ones. One of them is a bit trickier, but it's pretty much the same because you have this recirculation. So yeah, I'm going to give you 5 minutes to tell me which are the terms that should be written here. If you have questions, please go ahead and ask. So 3 minutes and no questions. Anybody wants to try to come out with an answer? Okay. Couple more minutes, and then I will show the answer myself, which is not fun. Come on. All right, then. Here it is. So nobody wants to say anything. You already have the answer in the screen, but anyway. Well, in the case of the first reactor, we're going to do exactly the same thing that we have here, but because we have a recirculation, we have two different flow rates to consider. So the first term that you have here is basically the same one that you have in the effluent in the previous example, but you need to add this recirculation to the influent term. So QR divided again by the volume. And in this case, of course, the concentration is different. It's not C in, it's C2, which is the concentration that you have in this flow rate here. So this is everything you need to consider when you have a recirculation. And in the case of C2, because Q1 is already Q in plus QR, and you only have C1, the equation is exactly the same as the one that you had in the second reactor. It doesn't matter if you have a recirculation coming out later on because you have Q1 and Q2 anyway. Okay, I didn't get an answer, but is this understandable or a bit clear for most of you guys? All right, then. So I'm going to keep going. And before I go back to biological systems and defining reaction terms and stoichiometry and all this stuff, I want to define quite a few things because many times this is not clear, and not only for students, but also for people that are not very much into this kind of modeling exercises. So first is the difference between an extensive and an intensive property. An extensive property depends on the size of your system, okay? For example, mass. If you have a given mass and you increase the size of your system, you can have more mass. An intensive property is normalized. A concentration, for example. If you have 1 gram per liter in a 1 liter reactor, if you increase the size of the reactor to 1 cubic meter, you're still going to have 1 gram per liter of concentration. The mass analogy doesn't work because mass, again, is extensive. The advantage of using intensive properties, which is what mostly we're going to be dealing with, if you go back to this is a concentration, right? The main reason we're going to do this is because our models are applicable to systems of different sizes if we use intensive properties. So most of the time, we're going to be working with this. And it's a very important difference because if you start defining a model in mass terms, it's only going to be applicable for the size of your given system, which can be annoying. A state variable. So a state variable is something that defines the state of your system at a given time. Again, in our case, most of our variables are what we want to predict. In this case here, for example, a concentration of a given species in your reactor. That is the state variable that you want to predict with your model. Important couple of things because they are not interchangeable. A variable, a parameter, and a constant, they are not the same thing. And many times they are treated as they are. So again, a variable is what defines the state of your system. A constant never, ever changes. This is very obvious of the name, but many times you will see works where constant are being calibrated in models, which is weird. You don't change the number 5, right? Gravitational constant, the Planck constant they're fixed. The same applies for thermodynamic constants. You don't change those. And it's really nice actually that they are constant because it means that you are reducing the degrees of freedom that you have in your system. And if you are used to modeling, that's a very nice thing because it means that there are certain things that you do not calibrate and just forget about it. And a parameter is what defines your model, along, of course, with the model structure. That, again, a state variable is what defines the state of your system. A parameter is what defines your model. It's not the same thing. I go back to, thanks, Jerome, for introducing monad before. A parameter is the maximum growth rate, for example, or the saturation constant in the monad equation. So those are parameters that we use to define our model, whether it's the kinetic or the stoichiometry. This, again, for me, the difference between variable and parameter is particularly those two, which are many, many times used interchangeably. They are absolutely not, and it's very important to keep that in mind. So, Alex, I think you were asking about the reaction terms. That's what we're going to be focusing about now. Again, before, it's simple mass balancing, so influent and effluent. What we struggle the most is with reaction terms, because that's where our biology is what actually makes a difference in our reactor. So, again, what this represents, it's what is produced or consumed in our mass balance. Think about any chemical reaction that you can think of. That's where those conversions will be considered in. There are two things that we have to define. The stoichiometry, of course, how much is produced from a given substrate. And as Jerome was mentioning before with monokinetics, the kinetics, so how fast. In steady state is a different thing, but you need to consider, of course, that many times kinetics and different reactions will happen at the same time. So knowing how fast a reaction occurs is, of course, very critical. I already warned you that I was going to repeat myself. Every reaction must be balanced in terms of everything that you put in there. So if you're assuming biomass, if you're assuming whatever you want to name it, any component needs to be balanced. And that applies for any conserved property. So, of course, elements need to be balanced around. COD, chemical oxygen demand, needs to be balanced around. And of course, charges need to be balanced around. You cannot have unbalanced charges in your reactions. I said before that I was going to talk about a matrix. This is the simplest way, the simplest reaction matrix that I'm going to show today. So if this is not clear, understanding what comes later is going to be a bit difficult. So bear with me. And please, if you don't understand this, don't hesitate to stop me. That's what I'm here for. So what we're going to have in this matrix is first the first row is always going to be names. So in this case, imagine that you have a substrate S that is being transformed into a product P. The first row is always going to be all the state variables, not parameters or anything else, state variables. So the state variables are always going to be your chemical species, for example, or anything involved in your reactions. So in this case, you have one substrate and one product. Those are your state variables or your components, which is the same. And that's the first row that you're going to have in this matrix. Okay. Any other row that comes later on are going to be all the reactions that are happening in your model. In this case, you only have one reaction, which is S becoming P, right? What we do here is we fill these gaps with our stoichiometric coefficients. That's everything there is to this matrix. By convention, you got negative values for substrates and positive values for products. As here is -1, and here there is a 1 here, and there is a 1 here. This is a substrate. The stoichiometric coefficient in the reaction of component S is -1. That's the value that we put here. For the product P, the stoichiometric coefficient in the reaction of P is 1. That's it. In the last column, after we have put all our stoichiometric coefficients in different columns here, in the last column, we put the rate equation. So in this case, it's first order. But we're going to get into that later on. First, what I really think it's important here is that you understand how this stoichiometry is defined. So -S minus P. How are we going to do this? If we want to include this in our equations that I mentioned before, if we want to know the difference in mass of S over time on difference mass P over time, the only thing we need to do, and here I'm only going to put the reaction term, is I don't have it. The only thing that you need to do here, this basically what you need to do is you multiply the rate by the stoichiometric coefficient, which is why this matrix is so useful. Here is pretty obvious. You take the stoichiometric coefficient that you have here, and you multiply this by Ks, and that's what you get. For P, in this case, is 1 multiplied by Ks. You can laugh at my writing skills on PowerPoint. It's okay. So the reason this is so useful is because here is relatively easy to see, because you only have one reaction and 2 components. But when you start having 10 components and 6 reactions, knowing what you have to put here is not straightforward at all. If you look at the matrix, you can have a look at it straight away here, and you will need you know that for S, the only thing that you need to do is to get all the rows where you have S with an stoichiometric coefficient and multiply that by the rate of each of the reactions. And that's going to be your reaction term. Are we kind of okay until now? Give me heads up or ask questions. Awesome. Thanks, Alex. Okay. Okay. Much better than before. Nice. Okay. Let's keep going then. As I was saying, don't hesitate to stop me at any time. If I manage to put the laser again, yeah. So what happens in biology is that at some point, I guess you already realized that, but generally biological reactions complicate things in terms of what's happening. And mostly if you have mixed systems, only what you have here is that if you have S that becomes P, so this reaction here, but this is performed by a microorganism, of course, you have the biomass growing. This biomass that grows as S is being converted by P by a certain bacteria is what we call X. Generally, standard use of nomenclature, any particulates, so solid stuff that you have in your model, is represented by X. So in this case, we're going to assume that X is your biomass and is the one that is responsible for transforming S in P. Okay. In this case, before I jump into the matrix, I didn't think about that sentence before I said it, but you have it here. There are two considerations that we have to think. And it might seem a bit counterintuitive. I hope it's going to be okay. So when you have a certain biomass growing on a given substrate, part of that substrate is going to go into your product, and another part is going to go into biomass that grows, right? So let's say that we have, I don't know, a fermentation reaction. And you have glucose that is becoming acetate and biomass. I'm just oversimplifying things. All your substrate is not going to end up as acetate because part of the substrate is becoming biomass. And on the other hand, if you want to grow biomass, you're not going to get all your substrate transformed into biomass because some of the substrate is also going to get transformed into acetate. To avoid having, let's say, many open stoichiometric parameters in your system, what we generally do is we use generally what we call a basis of calculus. And there are two ways of doing this. One is what we call uptake models. And generally what we assume is that we have 1 gram of substrate. I'm going to do the mass balance in COD terms. Out of this 1 gram of substrate, a fraction that we're going to call Y, because it's not random, is biomass yield, is what we generally, so that's the amount of biomass that you can make out of 1 gram of substrate. So a part of this gram of COD is going to become biomass yield, and the rest, so 1 minus Y, is going to become the product. So if I go back to the analogy of acetate and biomass, 1 gram COD of glucose is going to make Y grams of COD biomass, depending on this stoichiometric coefficient that we call the yield, and the rest is going to become acetate. This enables us to only have one unknown, let's say, which is biomass yield. I don't want to get into catabolism and anabolism, but basically what it says is that, of course, you have one part, which is catabolism, that is used to make energy, and anabolism, another part, which is Y, of course, that is becoming the biomass. Important thing is that we have two different ways. One is uptake, which assumes that we have 1 gram of COD as substrate, and then calculates Y accordingly. And we have also growth models. All these growth models use growth rates, which is what they are popular. And it's exactly the same thing, but instead of assuming that you have 1 gram COD substrate as basis of calculus, you assume that you are making 1 gram COD biomass. So basically what you're doing is you're dividing all these stoichiometric terms by Y. So you can get a 1 here. So if for uptake, you had 1 gram of substrate here, in growth models, you have 1 divided by Y for the substrate. For the product, you have 1 minus Y divided by Y, which is what you see here. And for biomass, you have 1 gram COD. I would like to say that we agree in which models we use most of the times. We don't. Some people like uptake models. Some people like growth models. It really depends on what you want to do. The important thing to understand is that it's exactly the same thing. You just are taking different bases of calculus. In one case, 1 gram of substrate gives certain products, and so 1 minus Y product and Y biomass. In another case, you divide everything by Y, so you can get 1 gram COD biomass as basis of calculus. Hope this is somehow clear, because that's how this is going to look like now. I'm going to assume that we have uptake models, because again, that's my personal preference, but the only thing that you need to do is divide by Y, as I will explain later. That in this case, so I'm saying we not only have S becoming P, we have S becoming P and biomass, which is the reaction that is happening in our system. So we need to add, we not only have S and P as we had before, we have S, P, and X. And the stoichiometric coefficients are basically the ones that we just defined here. We are using an uptake model. So this is the basis of calculus that we are assuming, -1 for the substrate. And by definition of yield, if we have -1 grams of substrate, we have Y grams of X, and the rest goes to P. So 1 minus Y. That's it. If we use a growth model, it's exactly the same thing, but the basis of calculus that we are using is 1 gram COD for the biomass, X. So basically you divide, again, everything that you have here by Y, and these are the stoichiometric coefficients that you have here. Okay. Something that previously, when I gave this lecture, didn't do was this. I've been talking about COD quite a bit now. This is chemical oxygen demand. How many of you are familiar with this? Give me a heads up. Okay. Okay. So most of you are. That's great. I'm going to go fast through here just in case not everyone knows what this is. But the main reason this is very important is because it represents the amount of substrate that is actually available for biomass to grow on. Again, it's very useful because it represents, again, chemical energy the biomass can be used, but also because we can measure it. And not only that, it's a preserved property. So if you do a mass balance or a mass balance over COD, it needs to close. Otherwise, you're doing something wrong with your model. Very fast, because again, not everyone replied. What you're assuming is that you are oxidizing everything in your substrate. So all the carbon goes to CO2, hydrogen goes to water, and sulfur goes to sulfate. Because the way we measure it does not oxidize ammonia, by convention, ammonia is left reduced in COD terms. Oxygen has a negative COD because it's the oxidation agent, and again, it has to be preserved. So if we have something that has a positive COD, you need to have a negative COD somewhere. And because ammonia is left reduced, so we assumed this is a 0 COD, more oxidized nitrogen species have negative COD. This is important for the calculations that we will do later on, balancing COD. And again, it's a preserved property that can be used in mass balances, and it's very useful for biological growth. So this is mainly why we use COD. All right. So now that I talked a bit about stoichiometry, we will do a couple of exercises later on. Now I'm going to talk about growth kinetics. If you remember, before I mentioned, there are two main things that we need to consider in the reaction term. One is stoichiometry, so how much product do we have from a certain substrate, and the other is how fast the reaction happens. For most cases, it's either first or zero order, depending on substrate levels. And again, Jerome explained monokinetics, so I'm going to go relatively fast with this. What generally happens is that the more food you have, the faster it grows, which is, so this is the uptake rate, so how fast the bacteria are growing. If you add more substrate, at low substrate concentrations, the response, basically there's a kind of a linear relationship. If you have more substrate, you have more food, you have faster growth. But this has a limit. If you add more substrate after a given amount, you approach basically saturation. And bacteria, even if you provide more substrate, more food, they will not grow faster. They reach the maximum uptake or growth rate. If we combine those two, we have again the Monod equation, which is what Jerome was mentioning before. You have this sort of linear behavior at the beginning, and then you have this saturation zero order. This is the general expression. I always like to mention Michaelis-Menten here because most people have studied this at some point in their career, not necessarily monad, but it's exactly the same equation, but because in biological reactions, the reactions are autocatalyzed by the biomass, you need to include the biomass terms in the Michaelis-Menten equation, which is basically where monad comes from. I will go back later on to what these two parameters mean. Here I'm using K, which is the uptake rate, or R, which is kind of the same thing. As I was saying before, the only difference between growth models and uptake models is that you divide by the yield. So if you are more comfortable working with growth rates than you are with uptake rates, you only need to multiply these values by the yield and you get your growth rate. As I was saying before, using one type of model, so either it's growth or uptake, is exactly the same thing. You are using a different basis of calculus. So if you don't like uptake rates, you just multiply them by the yield, and you get your growth rates. Easy enough. So monad works, fair enough, but there are many things to consider, and you might know them already, but there are many things that affect our growth rates, not only the substrate. So of course, you have the biomass. As I was saying, in monad, you have the biomass concentration, already considered that. You have the substrate, which again is in monad. But in some cases, you can have product-induced inhibition. So if you accumulate too much product, you have less energy available, and this can affect the growth rate. Most of you might be familiar with the principle of Le Chatelier. It's exactly this. Temperature also affects growth rate, and also the pH, and many other factors. So in most cases, we will use monad to models, but depending on the objective, again, of our model, we might need to include different things. Going one by one, let's say that here we only have limitation by substrate, okay? So we have the monad law. Just to show you that it's exactly the same thing using uptake or growth rate, I just put a growth model here. The equation is exactly the same thing. And what you have here is, so this value here, depending on the substrate levels. What you have here is a constant nu-max. This is just to show you how these parameters actually affect the model. Monad is defined by two parameters, which is the maximum growth rate that you have here, and the saturation constant. Here, nu-max, so the maximum growth rate is fixed to 0.5, and I'm going to be changing the Ks, so the saturation constant. And what you will see here is that as the value increases, of course, the asymptotic value that you have here, which is nu-max, is the same, but the behavior of the curve is totally different. The main reason for it is because while this parameter represents which is the maximum speed rate that a certain microorganism can get, what this parameter represents is how much substrate you need to get to that value. Being more precise, it represents the amount of substrate needed to get to 50% of the maximum growth rate. So in this case, it's 0.1. So pretty much the 50% value is around here. And as it increases, it will be going up and down. So as you can see, not only nu-max, but also Ks can have a very huge impact on the kinetics of your process. Just to show you that there are different expressions that we can use, and not necessarily we need to abide by monad. In this case, we have a situation where the substrate is not only needed for growth, but it can also induce substrate inhibition. There are many equations that we can use. In this case, I'm using Haldane, but there are many other. And what you will see is that the curve has very different behaviors depending on the values that we put to our parameters. So in this case, nu-max and Ks are fixed, but the Ki that we have here we are changing it around, and as you can see, the behavior is very different. All this to say that estimating these parameters is basically key and the main issue that we will face when we have these models. And for that, we need accurate data. And depending on the behavior that we know from our system, we will choose one equation or another, which is why knowing our system is very, very important. So, as I was saying before, temperature also plays a role here. And I'm not going to go through this in detail, but basically what you have is very typical behavior of biological growth with temperature, growth rate, so how fast it goes, increases with temperature. This is a ratio of the optimal of 20 over the growth of 20. And as you can see, it goes up until a certain value where the growth drops because basically you are denaturating all the proteins and biomass dies. Generally, we don't consider this section because in most cases, we are not operating our system at values where we know we're going to kill the biomass. Sounds pretty obvious in this case. So we use Arrhenius, which is an equation that most of you must be familiar with from chemical kinetics. So generally, we assume that we are in this part here and that we are not operating on purpose our system at temperatures that are killing our biomass. Of course, we have equations to consider also these terms. For pH, it's kind of the same thing, but because pH, many times we don't control it, we surely need to consider this this inhibition ranges, let's say, zones. And most of the times we use empirical relationships that we know work, just the ones that you have here. So basically you have a region where basically you run on optimal conditions, usually it's neutral pH. Of course, it depends on our system. But if we are talking about the neutrophile, this is the optimal region. If you go up pH values above that, the performance drops, so the growth rate drops. And again, if you're into acidic values also, the growth rate drops. So if we go back to this, we have, again, the two uptake or growth models for our model reaction, which is S becomes P and biomass. Stoichiometric coefficients do not change, but in this case, whether it's uptake or growth model, we will have our Monod equation here, either with the uptake rate or the growth rate. So this is by far the most common representation that we will have of our bioprocess models. And just to show you where this comes from, this is very typically used in most bioprocess models. This is old because Peterson metrics are quite old. We are not reinventing anything here. And what you see here basically is what I was telling you before. You have the components. So this is your biomass. You have the names down here if you want to have a look at them. But this is basically the name and the units of the state variable that you have here. So you got your biomass here, your substrate, just S, and oxygen, because it's an aerobic organism. That's pretty much it. Basically, what you see here is that, again, it's a growth model. So you're going to have one here. And because this is going to be getting consumed and this is going to be getting produced, it's not aerobic organisms that produces oxygen. What you're going to have here is a stoichiometric coefficients for products, so Y and Y minus Y. And then you have your Monod equation as you have just seen. What we have here is just biomass death, which is a very common reaction that pretty much happens in all our systems. So biomass dies as it grows also. And we need to consider that generally first order reaction and a -1. And we need to assume that it goes somewhere. In this case, in this particular model, we are assuming that the biomass is hydrolyzed instantly and is becoming substrate for further growth. Here we have the processes. So as I was saying, if you have more than one reaction, you just add ROS to your matrix, the growth rates, which you have already seen, and finally you have all the stoichiometric coefficients. And this is just very obvious, and most of the times we don't put this in our metrics, but the reaction term that you need to multiply this rates for basically are the summatory of all the stoichiometric coefficients and the rate for a given species. So this is the rate again, which is what you're going to be multiplying by all the stoichiometric coefficients, which are the new values here. All right, so we have been at it for 1 hour. How are you guys feeling? I don't know if before you were taking breaks or not. If anybody wants to, I don't know if Ellie is around. No, anyway, I think it's best if we keep going, if everyone agrees. If you need to take 5 minutes for a coffee or whatever, just let me know and we can stop too. Don't hesitate to let me know in the text or just open your mic. So what we're going to be doing now is we're going to use, again, the activated sludge model 1 as an example to define our reactions. In this case, well, again, most of you, I guess, are familiar with activated sludge for treating wastewater. Can you guys tell me if that's the case? Again, heads up. Nah, not very encouraging. Okay. Well, basically what's happening here is that we have influent wastewater going through an anoxic and an anaerobic tank. So this is where the biological reaction happens. We have certain recirculations and part of the biomass is sent back. So we can actually perform the reaction effectively, let's say, since the beginning due to biomass recirculation. I hope most of you are going to be aware that this process exists. But in our case, what we care about, again, are the reactions. All this recirculation, as I mentioned, as I showed you before, is just in a matter of mass balancing. So let's say that we have carbon oxidation. So heterotrophic growth, where organic matter in the wastewater is the carbon source, and we have aerobic growth. So oxygen is electron acceptor. Generally, what we're going to have is, again, soluble organic matter, which is biodegradable. I'm not going to get into hydrolysis and all this stuff, but you have organic matter that is used for getting energy, so catabolism, using oxygen as electron acceptor, and for growth, anabolism, with some nutrients in there. You get biomass, and biomass dies, and then it becomes, again, particulate, which is hydrolyzed, and you get some soluble organic matter. If we try to, let's say that we know that in our activated sludge process, this is happening. This is how we will proceed to define our model. So first, we identify our components. We know that we have biomass, which are heterotrophs, which is what you have here. We know that we have soluble degradable COD, which is organic matter that the biomass is going to be using for growth. We know that we have oxygen needed also, because if we don't have electron acceptors, the reaction is not going to happen. And we need some nutrients. In this case, we're going to simplify and just say that we have some ammonia. And we can define the reaction of aerobic COD oxidation. So we're going to have organic matter, nitrogen, and oxygen. And with those three, we're going to produce biomass, CO2, and water. That's pretty much it. Is everyone okay with this reaction? If you're not, let me know. At any time, again, because it's really weird to be talking to myself. The key issue that we have is that when we define our reaction, in most cases, we do not know the stoichiometric coefficients. Let's say that we assume that we have an uptake model. So we know that we have 1 gram COD of biomass here that gives Y grams COD of biomass. We have no idea how much nitrogen we need, and we have no idea how much oxygen we need. So we need to identify those stoichiometric coefficients. In the case of products, because again, we are most of the time using COD, we don't really care about CO2 and water. Although if we want to be precise and close carbon balances, of course, we're going to care about those. So let's say again that we have an uptake model or a growth model. If we have a growth model, we just divide everything by Y, and we know this stoichiometric coefficient for the substrate, and we know that this one is 1. At least we know those two in terms of COD balance. We still don't know A and B. So let's say that the yield, we know it, is the biomass yield. So per unit of biomass that grows, we're going to have 1 divided by H, or what is the same, per unit COD or of substrate that we consume, we're going to have Y gram COD of biomass. If we're going to know A and B, what we're going to do is mass balances. So continue to equations. What we have here is that, again, we cannot create nor destroy COD. It's a preserved property. And if we multiply all the coefficients for a given reaction by the amount of material C, either it's COD, nitrogen, carbon, whatever, in the products and the substrate, everything needs to adapt to 0. Mass conservation principle. If we do a COD balance over this reaction here, it's exactly what we get. We know that in this case, we got 1 divided by Y. In this case, the COD of ammonia is 0, so we screw it up. Again, COD has negative oxygen has negative COD, so we know that 1 gram of oxygen has -1 COD content. And because we know that +1 is the stoichiometric coefficient that we have here, we multiply all the stoichiometric coefficients by the COD contents of each of these terms, and everything needs to adapt to 0. If we do that, we get the stoichiometric coefficient B. Doing this kind of things is how we are going to define the stoichiometry of our models. Now we know B. If we define the nitrogen content in our biomass by any name, in this case is we call it IXB because it's what generally is being used in this kind of models, and you put everything you apply the continuity equation, you get the stoichiometric coefficient of A, of ammonia, and you take these two and you put them in here, and this is the aerobic growth raw that you have in the ASM1. So to make 1 gram of heterotrophic biomass, you consume 1 divided by Y gram COD of substrate, this amount of oxygen, because it's the B coefficient that you just identified, and we need also to consume this given amount of ammonia. If you do the same for all the other processes that happen, so anoxic growth, nitrification, death, etc., you fill all these gaps. Once you have filled all these gaps, you have defined your stoichiometric coefficients in your matrix. How are we doing so far? Questions? Everybody's okay? I'm going to assume everybody's okay, and I'm going to keep going. And at the end, you have an exercise that you need to perform. Okay. So now for kinetics. Again, this is the ASM1. For aerobic growth, you get exactly the same thing that you had before with monod, but in this case, we have 2 substrates. So either the organic matter that you need for bacteria to grow on, or oxygen. If you don't have oxygen, the stoichiometric, the aerobic growth will not occur. So you have 2 terms in the rate equation, in the monod equation. typical molecular kinetics, and both are rate limiting. And again, because we know this is stoichiometry, we know everything that we need to know for this aerobic growth. Just to show you that there are many different equations that we can think about. Anoxic growth is exactly the same thing, but we have an inhibition in case we have too much oxygen in there. So we just put what we call a switch function, which basically is just saying if you have too much oxygen, this reaction is not gonna run. Just for you to show that we have different tricks that we can include in our rate equations to know competition and the impact of different factors. And we put everything together. This is the ASM. It sounds a bit big and it can be a bit impressive, but the reason I wanted to go for this, and I always like to do it, is for you to show that if you understood what I just mentioned in the last minutes, you were able to understand this particular line here. So aerobic growth, all of those have different weird values here. They're calculated exactly in the same way. So if you understood how we did this, you just need to go through the reactions that are in the ASM, and you will definitely understand all these ROS that you have here. And the same applies for the stoichiometric, for the rate equations. You have ticks here and there, but again, the basics and the fundamentals of this are the same. So this slide is a courtesy of Jean-Philippe Steyer. And I particularly like it, not only because it's going to get your attention a bit after 1 hour of me talking to myself, but something very, very useful of modeling is that it's not only a tool for understanding, but it's also a toy. And the moment you understand this, you actually start getting the most out of your models. What we mean by toy is once you have a model that is ready, even if it's not validated, even if it's not calibrated, you name it, you have the main structure. Just play with it. Change parameters, change the effluent, change whatever, and see what comes out of it. That's going to allow you to not only know your model well and confirm that it works, but it's also going to give you plenty of ideas. So I really mean, and not only me, but most modeling people, we will always say, once you have a model, play with it. See where it goes. See where you're going to get results that you were not expecting. Because many times we calibrate our models and we are super happy because we are able to represent our experimental data. Okay, but what information are you getting from there? Play with it, simulate things, try weird stuff that you're not going to be able to try experimentally. So for me, this is a really, really key message. If you have a model, it's a really great tool for you to play with and get the most of your experimental data. So now we come to an exercise. From here on, I'm going to be talking much less. So I expect you to talk. Otherwise, okay, it's 10 to 4. We're going to finish a bit earlier than I expected. In this case, I propose that we don't stop at the moment because we are only going to be doing basically filling these gaps. But later on, I'm going to be asking you to code a bit, and I'm going to be explaining you a bit how a mechanistic model is presented in a simulation setting. If you want before that, we can stop, but I'd rather we do this first. So the reaction that we have here is the conversion of sugars. So soluble sugars, S for solubles and SU for sugars, into butyrate and formate. So both are soluble, S, BU, and SFO, by a macro that we're going to call X. XSU because it consumes SU sugars. Generally, we do that. If we have different biomasses, we name them according to the substrate that they consume many times. So the reaction is glucose. So 1 mole of glucose gives 1 mole of butyrate and 2 mole of formate. And these are the COD contents of these three molecules. This is a stoichiometric, so basically the Goodyear matrix This is a reaction rate. It's an uptake model, so we have -1 here. What I want you to do now is build these 3 cells in. In COD terms, build these 3 cells up. If you're able to do this, you understood more or less how the COD mass balancing that I was showing before worked, and the assumptions that we do in an uptake model, which is basically that the basis of calculus is -1. Having said that, I'm going to give you again 5 minutes, if everyone agrees. Let me know. And if you have questions, that's what I'm here for again. And what you need to do basically is say, the reasoning is basically, if y goes here, 1 minus y needs to go to these 2, right? And how would you define how much goes to each? It's basically given by the stoichiometry of the chemical reaction. So out of 1 gram of COD, which is basically, if you have this in mole, is the proportion in COD terms that goes to butyrate. It's 160 grams COD per mole divided by 192 grams COD per mole. So in this case, that's what you get. And in this case is 2, because stoichiometric, the molar stoichiometry is 2 multiplied by the gram COD content per mole. And that's it. If you do that, that's the fractions you get. And very important to check, which is always very useful. If you, again, sum all this up, you need to end up with 0, which is what you should be getting. But yeah, Soros, heads up. Okay, so now we knew, and again, this exercise, what I want to show you is that most of the times this biological reaction is something we know in our system, at least if we're doing a fermentation or if we're doing anaerobic digestion, whatever you name it. Most of the times you know the main chemical reaction that is happening, and you know, arguably, even if you can clump it as a certain group of microbes, you know who is doing your reaction. So this information, most of the times, you do have it. Once you have this information, defining a preliminary model is relatively easy, at least in terms of stoichiometry. The rate is a bit different. In this case, we are going to assume that we only have 1 reaction, and that's going to be it. So if you remember, now that we have the stoichiometry defined and we have our rate, what we need to define basically is our parameters, because they are the ones saying how that's going on or not. I'm going to tell you the parameters now. No worries. I'm just gonna give you a few values. You don't need to write anything down. So the value of that take rate is 20 gram per day. This is the saturation constant, so 200 milligrams COD per liter, and this is the yield. So this means that out of 1 gram, 0.1 gram end up as biomass, and 0.9, so 90%, and that ends up as product. So what we're going to be doing now is we are going to simulate a reactor performing that reaction. So we're going to have a fermenter with a volume of 1 liter, an HRT of 4 days. Of course, given that you have a certain flow rate, which of course is wrong. This is not the flow rate, it's 0.25. We'll correct that later on. But you have basically the sign parameters. You got a glucose concentration in the input and initial biomass concentration. And what we're going to do is you're going to solve the steady state for the system, and we're going to plot sugar, butyrate format, and all the different states that define our system, which if you go back here, we have 4 state variables. We're going to plot all these 4 state variables. And to do that, you need to create a function, etc., etc., etc. We will do it together, okay? And what I'm going to ask you to do now, and I'm going to give you a couple of minutes to do it, is open the files that you should have received this morning. And there are two different files. One is a run file and another is the model file. And you will see that there is run file 1 or something like that. Let me check the names. Yeah, so there is run file, model 1, and model 1. Only open those two, please, because the modifications to pass from model 1 to model 2, I'm going to be asking you to do them. So it's going to be a huge spoiler if you open model 2 straight away. So please only open model 1 and run file model 1. They are M files, so either you open them in MATLAB or in Octave, whatever you prefer. And I'm going to give you a couple of minutes. If anybody has issues opening those files, please let me know, because yeah, it's going to be annoying if you're going to do this part of the workshop. So at this point, I guess everybody has the model 1 files open, and there are two files, so the run file and the model file. What you should understand here is that the model file, so model 1 that you have here in the slide, that's your model. So that's what matters. And the run file, the other thing it does, it solves numerically the model using a certain algorithm. So we're going to start with the model file. So if you can all open that, what you're going to do is first, pretty much what we were doing before, you define your state variables, okay? So if we go back to the stoichiometric metric that we have, the state variables are the 4 variables that we have here. So sugars, butyrate, formate, and biomass. The way you do it is, and this is just how MATLAB or any, you need to know some coding tricks. Any state variable, in this case, because that's how we named it here, is going to be y. And y is going to be a vector containing the values of all our variables. But for us to understanding easier, we are just putting the first state variable in our vector is sugars, the second one is butyrate, the third is formate, and the fourth is biomass. This is defining the state variables that you have. The next thing that defines your model are the parameters. So here I'm just taking the parameters that I just mentioned before. So the U is 0.1 gram per gram. This is 200 milligrams COD per liter, which is a saturation constant for the Monod equation. And this is maximum uptake rate. So 20 gram per day. And again, then I'm just putting the stuff that I need to run the equation that I was mentioning before. So this is the intensive equation that I was saying at the beginning for each of these 4 variables. And what we need is the volume of the reactor, the influent flow rate, and this is very important, the initial concentrations. If you remember from the intensive equation that we defined at the beginning, what we need to define here is the concentration in the influent minus the concentration in the effluent. In the influent, because we want to convert sugars, in the influent, we have only sugars, which is why here we have the initial concentration of sugar in the influent, and then we have 0 for anything else. In the influent, we don't have biomass, we don't have formate, we don't have butyrate, but we do have a certain amount of sugar that comes into the reactor. Otherwise, we don't have any substrate, right? These 3 values are where we are putting it in here. Okay, I didn't provide exactly the initial flow rate, but I gave you the volume and the HRT. So this is very basic stuff. Once you have your reactor parameters and the state variables, what you can do is write the reaction rate. So the reaction rate, if we go back to our stoichiometric matrix, is this one here, right? So in the model, we have already this. We have all the parameters that we needed, which are written here, and we have the flow rates and all this stuff. Now we write the rate. which is what we have here. So this is Km multiplied by the amount of biomass, by the amount of sugars, divided by the saturation constant plus the sugars. And now what we need to do is write the mass balancing equation. So how each of these variables change over time, which is what we want to know in this models eventually. We want to do dynamic predictions. So we have the value of these variables here. We want to know how it changes. So we write the stoichiometric, the intensive mass balance equation here. And for the reaction term, we just multiply. The only thing we need to do is multiply the reaction rate by the stoichiometric coefficients that we had in the matrix. So it's R1. In this case, is R1 multiplied by -1 because this is the substrate, the sugars. For SBU, it was 0.83 multiplied by 1 minus Y. For formate, 0.17 multiplied by 1 minus Y. And for biomass is the rate multiplied by Y. It's exactly the values that we have here. So R1 multiplied by Y, R1 multiplied by each of these factors is the reaction term for each of the respective state variables. Of course, we need to do some coding tricks. When we define our model, we need to tell the software that this is a function that is going to have to run. And the way we do it, and this is just how it is, I cannot explain it any better way. We start by defining the output of the model, which is, again, this dy dt, the differences of the states over time. And then we need to put the name of the model and the input arguments, which in this case is going to be the initial value of the state variables. So y, the vector with all these state variables here, and t. And I'm not going to get into why we need to put this here. If we don't put this here, the model doesn't run, okay? We need to transpose the vector. So this is for the model file. Now that we have defined our model, we need to run it. And to run it, what we do is we create a file that is going to call this model. The run file has the following. So basically here, t and y is basically what we want to predict. So the values of the state variables with the time. And this is equal to a numerical solver, which is just ODE, ordinal differential equation. And in this case, 45, there are many others, but this one works in our case. And then what we need to do is between brackets, we need to give it the name of the function. So these are we call it the arguments of this function here. We need to put first, which is the function that we're going to be solving over time. So this function is called model1. This function you need to put model1 here. For how long? So the time span, as I'm saying, we are going to predict the behavior of our system for a given time. And if I go back to what I said before, it was solve the steady state over 10 days. So here, 0 and 10 between brackets. And again, between brackets, here we need to put, because what we are calculating is how the system will evolve over time, we need to provide an initial value for each of the states. And what we are saying is that basically what we have here. The initial sugar concentration is 2000 milligrams per liter, and the inoculant concentration is 500 milligrams per liter. This is exactly what we have here. We need to put it in the order that we have here. So if the first is SSU, the second is butyrate, the third is formate, and the fourth is biomass, these are basically the order that we need to put in the values here. So the initial value in our reactor is 2000 milligrams per liter of sugars, 0 butyrate, 0 formate, and our inoculum has 500 milligrams per liter of biomass. Yeah. A lot of information, and explaining coding is not particularly easy, mostly without seeing your computers. But what I want you to do first is to create this plot. And to do it, the only thing that you need to do is, I don't know, you have MATLAB, but in case you do, that's what I'm going to show. if you have opened your model 1 and your run file, so this is exactly what you had in the slide. Basically, all this, the only thing is doing is creating the plot. What you're saying here is basically create a plot that is named figure 1 that shows T and the first row of the Y matrix, which is, as we know from here, Y1 is sugars, Y2 is butyrate, Y3 is formate, and Y4 is biomass. So you're going to be plotting these 3 outputs for Y with the time, and then you're just going to put a legend so we can know which one is which. If you press run, which is the play that you have here, you should get a plot like this, pretty much. Please go ahead and try all of you, because this one is pretty much me doing the plot, but then I'm going to ask you to modify the model and do a new plot yourself. So if you're not able to run this one, it's going to be difficult. Let me know if you're able to get to this plot, please. So the other thing you need to do is open the run file and press run. Should be easy enough. Anybody getting it? Yeah. Okay, fantastic. So let's analyze our plot then. What this is saying is that from the beginning, we had an initial value of 2000 milligrams per liter, right? That's what we told the model. The concentration of sugar drops rapidly until we have very low values, basically around 8 milligrams per liter. And at the same time, obviously, we are producing a lot of biomass, so it increases from the initial 500 that we said, and we make a lot of butyrate and less formate, because that's how the reaction works. But at the beginning, we were not in a steady state in terms of biomass concentration. So even if biomass grows initially, because we had this 2000 milligrams per liter initially, because the HRT is 4 days, we are washing out a bit of biomass until we get to a almost steady state in 10 days, around 340 milligram per liter of biomass. This is a very good example for, let's say that you're running a system and you want to know which is the initial substrate concentration that you should use in your system, or which is the initial biomass concentration that you should put in your system to be as close as possible to the steady state, or you want to predict what the steady state is going to be at 4 days HRT, because you don't know if you want to start at 4, at 5, at 6, at 2. This kind of model is very useful for that, if you know the growth rate of your biomass. Questions? Are we good? Do you understand more or less how this graph works and how the 2 files, the run file and the model file, are structured? Everyone is kind of okay with that? Okay, then. What I'm going to do now is ask you to work again a little bit. And basically the idea is that, as I was saying before, a reaction that most of the times we have also in our system is biomass death. So biomass is growing, but at the same time, a certain amount is dying. And what we're going to have is our matrix, which is exactly the same as you have here. But you're going to have another reaction that is decay, so biomass death. The reaction is going to be pretty simple. You're going to have a -1 for the biomass, and we're going to have another component, which is that biomass, which we're going to call SI, which basically means a particulate component because it's an X, and Y of inerts is not going to do anything. It's just biomass that is going to die and it's going to stay there without making any reaction. And it's going to be washed out of the reactor. And it's basically going to be, we have 1 gram COD. We're going to assume that the composition is the same. So 1 gram COD of biomass dies and makes 1 gram of inert particulates. And it's going to be first order. So that's the reaction rate. What I want you to do now is modify model 1 and include this second reaction. You're going to need, of course, the value of this kinetic parameter, and is 0.1 day minus 1. I'm going to leave this here, and I'm going to let you do it. Ask me questions at any time, and do not open model 2, because model 2 is a solution for this. So unless you really want to have a huge spoiler, don't open model 1. Come on, play the game a bit. If you were here with me, I'll know if you're opening. Okay. Now it's a bit stupid for me to ask this. I have to trust it. So basically what you need to do now is add a second reaction and a fifth state. And that's going to affect both the model file and the run file. Please go ahead. I'm going to leave you to it, at least I would say 10, 15 minutes. And don't leave me here just looking at the screen. Ask me questions. That's what I'm here for. Well, if nobody else has questions, what I will tell you now that you have the model running, try things. If you feel like that's pretty much everything I wanted to go through with you guys today. So if nobody has questions, please, feel free to contact me anytime if you ever want to work with this. Myself and again with Eduardo and Ellie, we are working exactly on this for anaerobic digestion. So we are happy to collaborate and work. And if you ever want to do this yourself and you feel stuck and you have questions, contact us anytime. And if you feel like, go ahead and just take the model that you just created and play with it. Let's say that you want to optimize, I don't know, the HRT. See what happens if you reduce the HRT to 1. Stuff like that. And that's when things get interesting, because you can actually predict what's going to happen in your system just with a click in your computer. And that's extremely strong. Other than that, that's it from me. I don't know if anybody else has any questions. Otherwise, I guess you're free to go. Okay, then. Bye. Have a great evening, everyone. And see you around. Bye.